this Hamiltonian with this action here, we're going to have this eigenvalue problem, right? Okay. And it says that the instability comes from there being a possible negative energy state, okay, which is the superconducting state. And if there was a negative energy state, then all of the electrons are going to fall into that state by establishing this kind of group pairs. Okay. So that's what we're going to show here. Okay. So now, how do we solve this? Well, let's test this whole equation with this block. Okay. So k prime minus k prime, right? So the right hand side, okay, that's simple enough. ECE prime, correct? Okay, and the left hand side, this one is composed of two parts, right? There's a part coming from the free kinetic energy of the two electrons, which we already know to be twice epsilon k, right? K prime. Okay, and then the other part, oh sorry, so test this equation with this thing. The other part comes from what are the states linked through the interaction to this state, right? Okay. So this one is, the other part is going to be plus a summation over the possible k states, okay, ck times the matrix element, which is the interaction Hamiltonian represented onto these two plane wave gages. And we call that Vk prime k, going from k to k prime k. Okay? And because in the Bardeen-Pines interaction that we roughly talked about here, we saw there was a possibility for an attractive interaction. And to simplify the equation, to simplify the algebra as much as we can, I'm going to say that in the problem at hand, we're going to take this to be 0 mostly, and then to be non-zero, okay, to be a constant, an attractive constant between h bar omega d, between the range of the Fermi energy plus minus the highest energy of the phonons, which is what we talked about over in the first part, right? We said that that kind of interaction is going to link states that are roughly this much away from the surface of the Fermi sphere. So the most possible way you can do this calculation is like this. Okay, and it turns out that this is actually quite good, and you can make measurements to determine what is effectively V naught. Okay, so let's do that. And then because we said the Fermi sphere is isotropic and these things don't depend on direction, okay, we're going to turn the whole thing into a summation over energy. And because things are so close together, we're going to turn the summation into an integral. So, oh sorry, I forgot to write the ck prime here. So now, if I try to solve this equation, I can write ck prime is equal to minus 2 epsilon k prime minus e v naught. Okay, and then an integral from 0 to h bar omega d. Let me explain the notation in a minute. Oh, sorry. So now let's just rearrange some terms. Okay. So what we find is ck prime is equal to minus v naught summation over k. ck 2 epsilon k prime minus e. Right? Something like this. Okay. Now let's turn this summation into an integral. And in doing that, going from a summation over k to a summation over energy, and we're going to do a change of variable, you need to multiply by the density of states that goes between them. Right? Okay, so what that ends up being is ck prime is equal to minus v naught. Okay. I'm going to put the Fermi energy as the zero as the zero energy of reference. Okay. So the summation goes from the Fermi sphere from the Fermi sphere up to here. Okay. And then the integrand is equal to 2 epsilon k prime minus e. And then up here we have the density of state as a function of e. Okay. And this should be the density of state as a function of e divided by times like k. Something because we're summing over all the k. Oh, never mind. This is just the density of state. E epsilon k prime, and then d epsilon. Something like this. So now I can get away with replacing all these things. So c of epsilon is equal to minus this. Okay. And inside I'm going to write c of epsilon prime will be 1 over 2 epsilon prime minus e, and then it's what else? What else do we have? d of epsilon prime. Right? Something like this. Okay. So now I'm going to say that this thing over here is a constant also the Fermi surface. Okay. Constant. Oh wait, this one should be 2 epsilon, right? Okay, yeah. A constant. So d of epsilon, I'm going to approximate as the density of state at the Fermi surface, which for now is d equals to 0. So this being a constant can be taken out of the integral. Okay. So c of epsilon is equal to minus d of 0 v naught 0 equal to d. What gets integrated over here is just this c of epsilon prime d epsilon prime. And this thing, okay, if you look here, this is k prime, right? So this is 2 epsilon. This is not within the integral. This is actually on the outside over here, right? Okay. So basically now our goal is to solve this equation. And to solve this equation is easy enough. We just integrate this side with respect to epsilon from 0 to h bar omega d. Okay? That integral is going to cancel this one because that's just the difference of dummy variable. So now, if I do this integral over this side, this gets integrated, but these are constants. And then this just carries over. Now, this term and this term, there's no difference, right? So we just cancel them. Okay, so we get that the energy eigenvalue is solved by setting this integral to 1. Okay. So 1 is equal to minus d naught. And everybody knows how to do this integral. This is just logarithm. Okay. So we get that when I rearrange some terms, we can get E is equal to the magnitude of E is equal to 2 h bar omega d, and then e to the e to the 2 h bar omega d divided by whatever is here. E 0 d naught. Just this. Okay, so if we did that integral, we find this is the answer. So now we take the limit in which this this interaction is very weak, which is true. This limit, we take the v naught going to 0 limit. Okay. We find that there is still going to be a negative energy solution, which is E is approximately equal to minus 2 h bar omega d to the minus 2 over. Okay, so we find that this is the negative energy solution, and the whole thing is done by thinking about the problem at 0 temperature right now. Right? At 0 temperature, we sum from 0 to h bar omega d because of the presence of phonons, these states which are in h bar omega d around the Fermi sphere is going to be linked. This is what we're doing here. Okay, so this is the problem at t equals to 0. Now, what about finite temperature? And what's going to be the problem at finite temperature? We still have that picture where this phonon-mediated interaction is going to link the entire Fermi surface. But at finite temperature, states above the Fermi surface could be occupied because of thermal excitations. Right? And we know that roughly about kBt around the Fermi surface, there will be a probability of excitation. Okay. Now, if that state is already occupied, okay, so we start from some k minus k state. Okay, to be linked to the k prime minus k prime state by this interaction, we first need the k prime and the minus k prime state to be empty, right? Because otherwise the electron cannot scatter into these two states, correct? Okay. So what happens at finite temperature is this thermal excitation removes some portion of the states being linked. And as the temperature goes higher, more and more are being removed. And this is dictated by the Fermi-Dirac statistics. Right? So what's the probability of a state being vacant, of a state at a certain energy to be vacant? It's going to be 1 minus the Fermi-Dirac distribution, e to the. So now if I reference everything with respect to the Fermi energy, this is going to be epsilon divided by L plus 1. Right? So now I rearrange some terms. This is going to be 1 over 1 plus e to the minus plus 1 over tau. So for this link to be possible, we need the k prime and the minus k prime state both to be vacant. Right? So what's the probability for that to happen? It's going to be this squared, right? Roughly speaking. So we need a factor of this squared, which is what we need to plug into this integral over here, right? So the integral that we get is one is equal to we need this squared. Okay. Now that integral is almost it's too difficult to do. So let's think about what we said before. We say that the presence of this non-zero temperature blurs the originally sharp Fermi sphere. Okay? And it occupies the Fermi. We can think about this as removing the possible states being linked from the shell over there. Okay? So let me finish right here. So if the shell up to h bar omega d is over here, at a temperature of kBT, at a temperature of T, we know that this inner shell is already occupied. So there's no possibility of scattering into these states or removing these states from the picture, right? So that is exactly the same as starting with this original integral and replacing this lower limit just with kBT, right? Okay, so now we can think about when does there cease to be a negative energy solution anymore? Okay, so if we want a negative energy solution, we are subtracting a positive number from the denominator here. So if there was a negative energy solution, this integral compared to when this is not there, this is going to be larger, right? Correct. Yeah. So now the threshold is being when this integral is equal to 1. Because now if I add some positive thing to this can no longer be equal to 1. I mean, this can no longer be satisfied. So let's find out what is the threshold. And you find, after you can go through this calculation by yourself, you find that the threshold is just roughly kBT is equal to the magnitude of E at T equals to 0. Okay. Which is what we started with, right? We started with saying that, if I think about this in the excitation picture, we have the holes and the electron branch, and there being a band gap formed here underneath, which is the superconducting state. Okay. And at a temperature in which the thermal excitation can excite electrons out of the superconducting state, then superconductivity is no longer possible. Okay, so that's the problem of Hooper instability. So now today, basically I've answered for you the question of why the superconductivity is possible. But we didn't go into any detail. The real physics lies all in that electron-phonon interaction thing, which we don't have time to derive. And you can look into that if you're interested. So, yeah, thank you for listening, and I guess this is the last lecture. Yeah, if you have more questions about your final project, you can email me, and we can meet individually. And other than that, I guess I'll see you in some other courses.
Okay.